Shanghai GDG is a very interesting developer community.
I'm glad somebody has asked this question.
This is where the magic happens.
This is primarily a question and answer show. So if any of you out there would like to ask questions.
Hey everyone, it's great to be here. I'm John McCutcheon, a developer programs engineer at Google. And my passion is to make games on the web better. And I'm going to introduce a really neat new way to do that, which is called native client acceleration modules. This is a new concept that doesn't exist, but I think it's going to really make some new experiences possible on the web. So what if you wanted to write most of your application as a web app, meaning you're writing it in HTML5, you're using JavaScript or Dart, but there's still a few sections in your application where you just can't extract the performance out of JavaScript or Dart. Well, you can get native performance where you need it with native client acceleration modules, which allow you to extend your JavaScript or Dart application with C++ code. So right off the bat, I want to show you an example native client acceleration module. We have bullet physics running inside an acceleration module, simulating about 130 rigid body objects at 60 Hertz. This is not possible in the browser as today, but what's interesting here is that the front end, all of the graphics that you're seeing are being drawn by a Dart application by making WebGL calls. The physics simulation is happening in a separate module implemented in C that transmits the updated physics objects' positions to the Dart application, which then draws them. So let me run it here. You're going to see a whole bunch of blocks fall on top of each other and then some balls land on them. Isn't this really exciting stuff? I mean, you can't do this in a browser today, but you can with native client acceleration modules. So some of you might be asking, what is native client? I've never heard of this before. Well, native client allows you to take your C++ code and compile it with a version of GCC, which outputs a native client executable and a manifest file. This manifest file can be included in your website with a single line of HTML code, which then allows you to launch an entire C++ application and have it run in the browser. So specifically, native client is a secure C and C++ runtime for the web. There's no chance that the C code could take over someone's computer or damage it. It's secured in a sandbox. But your existing C and C++ code works, along with languages like C# through Mono. And these applications interact with the browser to take input and draw by using the Pepper API. But what makes native client somewhat limited from the perspective of most web developers is that it requires the entire application to be written in C. So if you want to get involved with native client, you have to be a C programmer, which many web developers aren't. So can we provide native performance where it counts, but make it accessible to all web app developers? And yes, native client acceleration modules is exactly that. It allows you to write most of your application as an HTML5 application and communicate with these very fast C-backed runtimes that do some computation for you. So drilling down a little bit, we see that the HTML5 application talks to some kind of JavaScript or Dart library which manages the communication to the back-end acceleration module. So if you're a C++ library author and you want to expose one of your libraries as an extension to the browser, how do you go about doing it? It's very straightforward. First, you have to port your application to native client, which is very straightforward because almost all of your C++ code is just going to compile over. The only areas where there'll be any extra work is if you need to interact with any Pepper API calls, but that's a fairly straightforward port, just like porting to any other operating system. You then expose your C++ API as an interface of messages. And what this really means is that you're going to be doing a lot of JSON message parsing and construction. You could use any communication mechanism you want, but JSON is very convenient because the browser can consume it trivially. And because JavaScript applications execute asynchronously, you need to add a work queue to your C++ module where the JavaScript application can queue some work for you to do. You do the work, and then you send the reply back later on. Once that's complete, you write the other side of the coin, which is a JavaScript or Dart library, which does the communication to the native client acceleration module. To give you an idea, it took me 1 day to implement the acceleration module that we saw earlier of bullet physics. Just a single day to parse the messages and construct new messages to send back to the browser. And it was really straightforward. So if you're a web developer and you want to consume one of these extensions from a native client acceleration module, how do you go about doing it? Well, it's really easy and exactly like you would take any other JavaScript module that exists today. You include the script tag that references the API that you're going to be calling. And the one extra step is that you include the embed tag for the native client manifest. Once you've done that, you just make JavaScript calls as normal, and they just get routed into the C code in the back end. But that's invisible to you as a web app developer. So it's similar to using any other JavaScript library like jQuery. It's really straightforward. So what this is going to give us is 90% of your application is going to be a web app. But you're going to get the native performance where you need it, including bullet physics simulating hundreds of rigid bodies at 60 Hertz, blazing fast zip decompression, video encoding and processing, image processing, encryption, all of these very computationally expensive things that you can implement in JavaScript, but you're going to see a big performance difference between the native C code. So now I want to shift gears and talk about the back-end implementation of this system. So you remember this diagram from earlier where I'm showing the HTML5 application using the JavaScript module that they've included, which is shunting the messages back and forth between the native client acceleration module. So what I want to ask is, what are these messages and how are they transmitted? So let's get to it. All of the messages start with a message header, which is a serialized JSON string. It includes a command name, a request ID, and then an arbitrary set of arguments, depending on the command itself. But sometimes these messages are going to need binary data. And JavaScript has a mechanism of accessing binary data through something called a typed array. And so after the JSON message header is sent, subsequently the n number, where n could be 0, of typed arrays are sent afterwards. So depending on the format of the message, there might be 0 typed arrays following the header, or there could be 5. It's completely up to the implementer to decide the optimal way of structuring these messages. But they all start with a header and then optional set of typed arrays following that. So let's give an example. If I'm a JavaScript app developer and I just want to call this Fibonacci accelerator and get the 10th Fibonacci number, I make this single call in JavaScript. I tell it the nth Fibonacci number I want and the callback that I want to have fire when the result is available. But underneath the hood, what happens is a command is structured, and you can see that the command is fib, the argument is 10, and the request ID is 27. The request ID is used to connect the reply that will be coming later on from the native client acceleration module. This message gets packaged up and sent over to the acceleration module, where the acceleration module does its computation and figures out that the 10th Fibonacci number is 55. It then packages up this message and sends it back to the JavaScript side, with the request ID being 27, just like the original message, so that you can connect them on the other side and the correct callback is fired. It's a very contrived example, but this gives you the flavor of how this operates. So how are these messages sent? Well, they're sent with calls to post message, and post message takes these messages and they puts them into a queue that the web application consumes or the native client acceleration module consumes. So I want to talk about message ordering. Let's say I have a JSON message header and then it requires 3 typed arrays following it, but some other JSON message header gets in the way. It gets in the middle. The question is this possible? And if it is, how can we work around this problem? Well, it turns out that it is possible in one specific configuration. The configuration of where there's many native client acceleration modules embedded on a page, and they're all communicating back to the web application at the same time. Because there is only one queue for the entire web application, what can happen is that the messages will end up interleaved between each other. And so you'll get some of the green messages, and then you'll get the yellow and the red message, and then you'll get the tail of the green message. This would be very confusing for the web application, and we need to do something about this. So what you do is you place a router between the message queue and the native client acceleration module JavaScript libraries. And this router uses the event source element ID as a way to route the messages from this single queue to the specific JavaScript libraries. And this solves this problem. So now I want to talk about the performance of these messages, because if the performance isn't great, then this is just not going to work. But it turns out that the performance is actually, it's pretty fast, and it will be getting faster as we move forward. So what we're looking at here is a graph of the number of round trips in 5 seconds. So a message is being sent from JavaScript to the native client acceleration module and then back. How many times can this happen in 5 seconds? The x-axis is showing you the message sizes, starting at 16 bytes and ending at 16 megabytes per message. And the y-axis is telling you how many round trips. So until your message size hits about 4K, you don't really see much of a drop-off. It's between 25,000 and 30,000 messages in 5 seconds. But after 4K, it starts to drop off steeply, but it's only at message sizes above 256 kilobytes that you start to see the latency go beyond 1 millisecond for a round trip. Another way of looking at the same set of data is, what's the throughput? How much can you push through this pipe? And it varies depending on the message size. So if you send larger messages, you get more throughput. And it peaks at about 420 megabytes per second. But once you hit about 640K per message, 64K per message, you get pretty close to this maximum. So that's the sweet spot. If you can package up all your data for computation and the results in less than 64K, you're going to be great. So I'm going to just pause here and note that I ran these benchmarks on a machine running Chrome 21, Windows 7 with 64-bit, a Core i7 with 12 gigabytes of RAM. Benchmarking is difficult, and your operating system and hardware configuration will give you different results. So don't take this as the absolute truth, but it was true for my machine. So the native client acceleration module message system allows for many native client modules on a single page, which is awesome, so that the developer can mix and match based on your application needs. It offers low latency and high throughput, which is key. To make this a little bit more concrete, I know we looked at graphs and we saw that we could transmit 420 megabytes per second. What does that actually mean? Well, let's say you wanted to stream a 1024 by 1024 video at 60 hertz and just transmit the entire frame at a time, so no compression involved, just 60 times a second you're sending the 1024 by 1024 image across, well, that will use 60% of your bandwidth at about 240 megabytes per second. So you still have lots of room for other communications that need to happen and you'll have an 8 millisecond latency per frame, which is fine because since we're displaying at 60 hertz, 8 milliseconds is actually only half of the time that you have to display, so you won't even be an entire frame back. Another example, let's say you wanted to physically simulate 1,000 rigid bodies. This is something that modern CPUs can't even do at 60 hertz, but if they could, you would be using just 1.7% of your bandwidth available and with a 2 millisecond latency, which is awesome. So let's look at some case studies a little bit more in depth. So I showed the video earlier of the Bullet Physics acceleration module operating, communicating its results back to a Dart application, but how does this really work under the hood? Well, the Dart application sends an initial message, which is load this scene. And this scene includes a description of all the rigid bodies in the scene, where you want them to be, how heavy they are, how much friction they have, all these type of physical properties that you get. This gets sent to the native client acceleration module, which remembers the state of the scene. Later on, when your application is ready, it sends a step simulation message to the acceleration module. It says, okay, I want you to simulate the physics world and have it update so that it's 16 milliseconds in the future. It replies back with the set of transformation matrices after the simulation has been updated. Those transformation matrices can be fed back into the Dart application and used to draw the world as it is based on the state of the physics simulation. Then this loops. After we do that, we send another message back to the native client acceleration module saying, update the simulation, we get the new transforms, and we draw it, and we just keep looping. So let's look at the performance of a native client acceleration module built around Bullet to machine-translated JavaScript. So for those of you who aren't familiar with machine-translated JavaScript, there are tools out there that will take a C or C++ program and compile it to JavaScript, which is pretty awesome. But how does the performance compare when you're executing that JavaScript that was generated by the tool versus a native client acceleration module? Well, what the graph we're looking at here, the x-axis is frames, the y-axis is microseconds to update the simulation state. So red is the JavaScript execution time, blue is the native client acceleration module. You probably notice you don't really see a lot of blue, and that's because the performance difference is so large that blue is just essentially at 0. I'll zoom in a moment and show you the true difference between them. But what's interesting about this graph is you see these two huge spikes where the JavaScript is just like, even for its own baseline performance, is like many times slower for these like moments. And so the question is, what's causing this? And it's difficult to nail down exactly what's causing it, but there's two likely causes. The first is JavaScript is a garbage collected language. So after a certain amount of time, enough garbage, which is objects that are no longer referenced, accumulates, and what happens is the JavaScript runtime stops the execution of the program. It goes in and collects all of this garbage, frees it, and makes it available for future use. But what that means is that if that garbage collection ticks in the middle of your physics simulation, you're going to see a huge spike in the time it takes to update the world. Another cause is that because JavaScript is a JITted engine, what it does is initially it outputs unoptimized code. And then it collects statistics like, hey, every time this function gets called, the first argument is a string. And then it outputs optimized code based around that assumption. But what's inside that optimized code is checks that that assumption is true. The moment that assumption is not true, it pulls a parachute out and it goes back to the non-optimized code. So what we're seeing with these two spikes could either be really extreme moments of JavaScript, garbage collection, or some assumption is being broken and everything is getting de-optimized and then re-optimized. Eventually it stabilizes, and when we zoom in, we can actually see the execution time for the native client acceleration module. In this specific example, it's about 100 microseconds per frame update, and you can see that it's very steady. Whereas the JavaScript update is 1,000 microseconds, or an order of magnitude slower, with these weird spikes. I mean, this was noise on the image that we were just looking at a moment ago, but you can still see that every once in a while JavaScript performance goes from 1,000 microseconds per frame update to 2,000 or 4,000. It's very bumpy. You never see that kind of variation with the native client acceleration module. So what about download size? These are web applications, and this is really important. If the JavaScript performance is not that great, but it takes only a fraction of the time to download than the native client acceleration module, maybe that trade-off is worth making. So looking at the uncompressed sizes, the acceleration module is a 3 megabyte download, and the machine-generated JavaScript is 2 megabytes. So we're looking at about 66% of the acceleration module to download the JavaScript. Compressed, it gets a little bit better. It gets close to about 2 times the download size for the acceleration module to 1 JavaScript module. So again, this really comes down to what's important here. If you have very light load and you can get away with using the JavaScript code, good, that's awesome, because it's going to download a little bit faster. But if you have something really heavy where this really matters, where it counts, when you need that native performance, the overhead is not that big. So let's look at another case study. Let's say you want to be able to zip and unzip things inside your web application. There are implementations of this in JavaScript, but again, as we'll see, the performance is just, it can't be matched. So the native client acceleration modules for the compressor and the decompressor are stateless. They're kind of dumb. They just accept a message, they take the uncompressed data, and then they decompress it. They take the uncompressed data and they compress it and they send that back to you as a message. The decompressor works similarly. You give it the compressed blob and it sends back an uncompressed blob. It's very simple. These acceleration modules have no state. They don't really know what's going on. They just do one thing and they do it really well. But what's great about the acceleration module framework is that you can include both of these on your page and send them a message whenever you need to. So let's look at the performance again. Again, you can see that the JavaScript implementation executes at about an order of magnitude slower than the native client acceleration module does. And again, you see that very rocky performance. It's not as consistently, the performance is just like, sometimes it's fast, sometimes it's slow with JavaScript, whereas with the native client acceleration module, it's much more stable. And looking at decompression times, again, you can see that the native client implementation is far faster than the JavaScript execution. So what am I saying about machine translated JavaScript? Well, first of all, it works and it works really well. Depending on your needs, it might be a great solution for you. It's pretty amazing that you can take a C++ program and get a working JavaScript program out of it. It's kind of mind-blowing. But what I'm really showing with this performance comparison is the difference in execution time for a JavaScript JIT engine versus native code running in the native client sandbox. So that being said, native client acceleration modules are an order of magnitude faster than the JavaScript equivalents, and they offer consistent performance. And for interactive applications like a physics simulation, consistent performance is key. If there's a frame that's 4 times slower than the previous frame, it really gets weird and the experience is just not there. So wrapping up, I first want to talk about some concerns. So one, currently native client is only available in Chrome. But as I've shown, machine translated JavaScript can offer the same functionality, but just at a performance penalty. So for web browsers that don't have native client yet, you can fall back to the machine translated JavaScript implementation. Another concern, it's early. There's no shipping acceleration modules out there. There's just some prototypes and a bunch of sample code. But this is the perfect time to help out. You can help make this a reality. So the third concern is that there are certain classes of applications, maybe a spreadsheet, where if you need to keep all of the cells in the web app side and all of the cells in the native client side, or constantly be communicating back and forth with each other, the performance gains here are not going to be as drastic as we're seeing. But the native client acceleration module framework is really designed for these, like 90% of your application is a web app. 10% of it needs to be really fast, and you want it to run in a native client acceleration module. So native client acceleration modules are going to allow us to bring new types of experiences to the web. Things that you can do today, but you can't do it fast enough to make it a great experience. The usage for you as a web developer is really straightforward. It's just like including any other JavaScript library. You don't have to worry about the C implementation or anything like that. It's taken care of for you. You just make some function calls in JavaScript, and it works really fast. So 90% web app, native performance where you need it. That's what you're going to get with native client acceleration modules. So to do. You've got to go and get the native client SDK. You can get that from going to www.gonacl.com. Clone an example native client acceleration module. You can get that from the URL there. It's coming out of my GitHub. You could take that and use that as the base to start writing your own. And join the discussion. Participate in the mailing list and start talking with other people who are implementing native client acceleration modules and come up with better ways of doing this. Thank you. I'm John McCutcheon. You can read my blog at johnmccutcheon.com or find me on Google+. Check out all the code I read on GitHub or check me out on Twitter. Thank you.